Okay. Well, it's 4 o'clock, so I'm going to start. If you student join, you're more than welcome, but got to start. So I'm going to start with prayer. Father God, again, I thank you for another session for this math class, and I ask your blessing upon all the dear students. Guide and lead all of them, guide and lead me, help me, for without you I can do nothing. And may you bless our time and help us to learn these principles of mathematics to gain some understanding of your greatness. Lord, thank you for all these dear students. Bless them as they partake these assignments and participate in these courses, in these classes, and help us to learn how to use mathematics in gaining a better appreciation of your knowledge and your beauty, and also use it for ministry. We commit our time into your hand, and we pray all these things in Jesus' mighty name. Amen. Hi, hello, how are you?
Hello, Professor. I'm doing good. How about yourself?
Good to see you. Thank you for your reports. You're doing very good. I enjoyed reading them. Any questions before I go to the lesson for this session?
No, not right now. I'm looking forward to it. I've been doing the reading for this week, but I haven't had a chance to look at the videos. I'm actually going to look at them after this class tonight. So I just wanted to sort of go over what we're going to go over today, and then right after the class, I'll look at the videos.
That's fine. No problem. Okay, let's go to the share screen, and let me go here. And oops, maybe there is. I'm trying to maximize this. I guess that's it. That's the full maximum that I can go. Anyway, you can see the screen, can't you? Yeah.
Yeah, I can see it. Actually, I think if you push on the bottom right, there's like a presentation mode. Are you trying to?
Oh, yeah. You're right. That was it. I was looking at the wrong place. Yeah.
On the bottom right, on the towards the bottom of the screen.
Yeah.
The little monitor is at. Go a little bit to the left.
Oh, yeah. Okay.
Yeah, slideshow. Yeah, that's what it is. Yeah.
Okay. Yeah, that was. I was trying to find that. Okay, thank you. Today we are going to focus on sets, and then from there we go to the different numerical system, which are basically different sets, mathematical sets. We can have sets of different things: animals, plants, tools. It's just collection of bunch of stuff together that are somehow related to one another forms a set. A set is a collection of objects which are called elements or members. So what goes in a set is called element or a member of the set. A set is well defined when what it contains are clearly determined. You know what goes into the set. Then we can say that set is clearly defined. For example, a set of days of weeks, Monday, Tuesday, Wednesday, so that's a well-defined set. Now, there are three ways that you can indicate a set. You can describe it, you can use a roster form, or you can use a set builder notation. Now, I will talk about them. Let's say, for example, let's do this. We want to write a description of the set containing the elements of Monday, Tuesday, Wednesday, the different days of the week. So, well, basically, it's just you describe that set The answer is the set is the day of the week. That's it. That's description. Now you can use a roster form to also define a set. And when you want to use a roster form, basically, it just, again, like learning a language, you have different signs and symbols you got to use. You have these braces here, and you call them, and when you use that, you call that way of description of a set a roster form. The elements are in that braces and are separated by a comma. For example, this set here, you have these two braces and then 1, 2, 3. That's a roster form, and the elements of this set are these numbers 1, 2, 3. But you cannot use parentheses or you cannot use brackets. These two are not the proper way to show a set in a roster form. You need to have the braces. Now, usually the name we generally name the set is generally named with capital letters. For example, if you want to have a set of natural number or counting number, usually the name that is used for it is capital N. Like here, oops. This N is a set of natural numbers. 1, 2, 3, 4, 5, and then comma, and you see these 3 dots, the ellipses, indicate that this is continuous. It's an infinite set. These are the elements in the set.
Quick question. So you said that it's the braces, it's not the parentheses, right? It has to be those braces right there.
Yeah, that's right.
Okay.
In order to show it as a roster form.
Got it. Okay.
Then, let me bring this up. For example, if we want to express the following in a roster form, let's say we want to describe a set A, set of natural number less than 5. Okay, so let's go here. So the elements would be 1, 2, 3, and 4. It has to be less than 5, natural number. A roster form for representing this set would be this: A equal these braces, and inside 1, 2, 3, 4. Now, let's say we said the second question is set B is a set of natural numbers less than or equal to 75. Now, this is important. Pay attention to this. Less than or equal. That means it includes 75. So you go 1, 2, 3, 4, then comma, then you put those 3 dots, the ellipses, and 75. In other words, you don't need to write all the way, all the numbers between 4 and 75. Those ellipses indicate the elements continues in the same manner, 5, 6, 7, and so on.
Does it have to be at least the first 4 numbers?
No, I would say at least the 3 numbers. The 2 would be too few because you want to see the pattern. So at least 3 numbers. But 1, 2, 3, 4 is fine, and then you go to 75. Or let's say
it has to include the number. So if it's equal or less, it has to include that number that we're talking about.
Yeah. When it says less than or equal to 75, you got to include 75. If it was only less than 75, then you wouldn't include 75.
Okay, that makes sense.
Then, or a set for planets in a solar system. So you call that set P equal. Then these are the names of the planet from sun toward going outward: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And I'm going ahead of myself, but the number of elements in a set is called the cardinal number of that set. No, okay, we will get to that. Now, the word inclusive is important. Expresses the, for example, when we want to express the followings in a roster form, we want to form a set of natural numbers between 4 and 9. So I don't want 4 and 9 to be included. I'm saying between 4 and 9. So if we set A, 2 braces, 5, 6, 7, and 8. Now, if I say set of natural numbers between 4 and 9 inclusive, that word inclusive indicates that you need to also include 4 and 9. And it would be 4, and as you can see in set B here, you have 4 and 9 here. So that's the difference between these two examples. Okay. Let's go. All right. Now, set builder notation. Another way to express a set is, another element, vocabulary terminology for set is called set builder notation or set generator. It may be used to symbolize a set and is frequently used that in algebra. A few things about set builder notation. One is this symbol, looks like an E or epsilon in Greek. It says this whatever is an element of. For example, when you have set A, which includes these elements 5, 6, 7, and 8, we can say 6 and then use this E or epsilon is an element of set A, or 6 is an element of 5, 6, 7, 8 because 6 is in that set. But for example, if you are talking about number 9, 9 is not an element of set A because it's not in one of its members. All right. Good. Let's continue. So,
if you're stating that it's not, then it's just that E with the slash going across.
Yeah, meaning it's not a part of that.
Okay.
So now we come a little bit, make it more a little bit complex, not a whole lot. If we want to use set builder notation and using algebraic terminology, okay, we have these braces. So it's a set of, then we put X here. If I write here, X means set of all X, and X can be whatever, numbers, people, planets, food, whatever. Set of all X. But when I put this vertical line here, vertical bar here, it means such that. Now I'm defining what goes into this set. I'm defining the limits of this X. X is, in this case, less than or equal to 2. This is a sign of less than, and when you see this bar here, means equal. That's a set of all numbers less than or equal to 2. So if it's a set of natural number, it would be only 1. Let's look at this picture, if you can see that. For example, the first one, X is less than A. X, this is the meaning of that. So we want a set of all X such that X is a natural number, is a member of natural number, and is less than 4. Natural number starts from 1 and it goes all the way to infinity, and no fractions, no nothing else. So all the natural number less than 4 would be, the set would be 1, 2, and 3. Okay.
Okay, so on that one, so I'm sorry, can you go over that? I get what you're doing there. Mm-hmm. It's less than 4. It's set of whole numbers less than 4. I guess what's throwing me off.
Okay. You see, this is set builder notation. If I am using set builder notation, for example, if a exercise asks you write a set of write this set in a set builder notation, you put these two braces.
Okay.
And then you say all x such that x is a natural number and x is less than 4.
Okay.
Now, if you want to write that in a roster form, you put the two braces. Now, in a roster form, you define this is an algebraic form. I'm not even identifying the numbers. Well, in a way I am, because I am putting these limits. But here in a roster form, I specifically mentions the element. I say all natural number less than 4 would be 1, 2, and 3.
Okay.
So if I go to the beginning, x is less than a. So yeah, if a is 4, then all the natural numbers would be 1, 2, and 3. Okay. Now let's make it a little bit different. All x is less than and equal to a. So set builder notation would be, again, you put two braces, all x such that x is a natural number and x is less than or equal to 4. So in this case, because of that equal, you include 4. Okay. Let's go to this one. X greater than a. X is all, and if I wanted, again, set builder notation, all x such that x is a natural number and x is greater than 4. So it cannot include 4 because I didn't say greater than equal or inclusive. I said greater than 4. So I start from 5, 5, 6, 7, 8, and then 3 ellipses, and means it continues to infinity. If I say greater than equal to a, would be all x part of a natural number, greater than and equal to 4. The only difference now, I have to include 4. You follow me?
Yeah, I'm getting it. I got it.
Now, let's look at these. It says, as you want to write a set for x, then x is greater than a, but less than b. Okay. So if I want to write that set in a set builder notation, again, I put the two braces, all x such that x is a natural number and x is greater than 4 and less than 8. That's the set builder notation. If I want to write it as a roster, what are the numbers greater than 4 and less than 8? 5, 6, and 7. So you would, that's what I write here. All right. Now, if I put equal signs, greater than equal, less than and equal, everything would be the same. All x such that x is natural number, greater than and equal to 4, less than and equal to 8. It would be like that, but now because of those equal signs, I have to include 4 and 8. That's inclusive, in other words.
I have a quick question. Okay, so I get on both of those examples. So for example, in the first column, which is the inequality symbol and meaning, how do we get 4 on the set builder?
Oh, that's given by the
okay. So that's what they're indicating on the bottom, and that's why we okay, yeah. I got you. Okay.
Yeah. So that's when the questions has to indicate that.
Okay.
So, okay. Now you can have one side greater than equal, or one side less than an equal. So when you do that, everything is the same. When I put the equal signs here, but not here, so I go 4, 5, 6, 7, but I don't include 8 because it has to be less than 8. If I put the equal sign here, it means all the numbers greater than 4 in this case, but less than and equal to b or 8. So it would be 5, 6, 7, and 8. Okay.
Yeah.
Yeah. Good. Let's go to, oops, cardinal number. What, when we talk about cardinal number of a set is, and we write it by this, n parenthesis a is a number of distinct elements in the set. In other words, cardinal number answer how many elements are in that set. And you write it like this: n parenthesis a is n of a. Let's look at, these are simple. Let's look at page 50 of our textbook. For example, page 50, if you look at example 8, it says if you have a set A, which these are its members, 7, 9, 11, and 13. What's the cardinal number? How many members are in that set? 4 numbers, 7, 9, 11, and 13. So the cardinal number for that set is 4. So you write n of a is equal to 4. Okay, you see that? Or if we go to set B, it has 0. Now remember, 0 is not nothing. 0 is a number, it is a member. So it contains 1 element. So the cardinal number for set B is 1. Don't think that 0 means nothing. Now, if we go to set C, it's in a roster form. It goes from 13 to 23. How many numbers are between, not in between, from 13 through 23, there are 11 numbers, 11 natural numbers. So we say the cardinal number, or n of C, is 11. All right. Set D is interesting. That's that sign, when you have a 0 and a slash going through it, it means empty or a null set. So it has no element. And here is the cardinal number 0.
So then on D, it would be 0 because it has that little, the slash. Yeah. Okay.
Yeah. Because that means null. And there's nothing in it. Okay. All right. Now, we have finite and infinite set. Set A is a finite set if n of A, or the cardinal number of A, is either 0 or a natural number. So you can have, like in the example that we looked, all those 4 examples are finite set, because it's either the number of elements is either 0 or a natural number. An infinite set is when it continues forever. Is a set that the cardinal number is not 0 and it's not a natural number. For example, if I write a set for all natural numbers, n, it goes 1, 2, 3, 4, 5, 6, and can continue to infinity. So that's an infinite set. A universal set is all the elements or members of any group under consideration. For example, an example of a universal set would be all the students at Southern California Seminary. That would be the universal set, because it includes all the students, part-time, full-time, male, female, graduate, undergraduate, whatever. All right.
So quick question. So in regards to, like, let's say this came up on a quiz or something, would you write out like n equals the braces and then all those numbers with the 3 ellipses and ask, is this what kind of set is this? And you would indicate infinite set, or I guess I'm trying to understand how We just want to know that that's an infinite set because it keeps going. I
Yeah,
guess.
yeah. If I write it like here, as you can see here, that would be an infinite set. But if I somehow limit that, let's say all the numbers from, like the example that we saw, between 13 through 23, that's a finite.
Finite.
Whenever you can describe the cardinal number as either 0 or a natural number, then it's finite. But when it's keeps going, it's infinite.
Okay, and in regards to that makes sense. Okay, and in regards to the universal set, how do we look at that one again?
If it includes it includes all the elements or members of any group. For example, all the students at Southern California Seminary. That would be the universal set because it includes all the members, all the students, whatever gender or graduate, undergraduate, part-time, full-time, it includes everybody.
Okay.
Now, when the cardinal number is infinite, then you write it like this. Aleph, this is an aleph from a Hebrew alphabet, null, aleph null. Okay. So, these are some of these things you got to keep in memory because it's just like any language that you need to have some vocabulary. You're learning these symbols as a vocabulary. Now, equality of set. A set, let's say set A is equal to set B when all the elements in set A and all the elements are in set B are the same. When they have exactly the same elements. Now, the order can be different, or it can even have repetition. But if all the members in one set is in the other set, then they are equal, exactly the same elements. And when the two sets are equal, we just put the equal sign. Set A is equal to set B. For example, if set A has, again, remember to put these braces, these are the elements, W, X, Y, Z. And set B has Z, Y, W, X. They are the same because they have exactly the same element, even though the order is different. Z is here in the first, Y is here, but Y is 2. But because they have the same elements, they are considered the same. Let's look at page 53, example 10. We have one set is 489. Is asking, is set 489 equal to 894? Yes, they have the same elements, even though the order is different. But the second example, example B, 135, is not equal to the set 0135 because the first one doesn't have 0. Okay. So now we come to subset. A set A is a subset of set B, and we write it like this symbol. This is a symbol of being a subset. If and only if all the elements of set A are also in set B. Now, set B can have more than elements of set A. Here we are not talking about equality. We are only saying whether set A is a part of set B. If all the elements of set A is in set B, then we say A is a subset of B. If it's not, then we put it like this. We write this symbol and with a slash saying A is not a subset of B. Let's look at page 57, example 1. For example, A is a set A is 1357, set B is 1357, 9, and 11. So set A is a subset of set B. All the elements in set A are in set B. We are not talking about equality. They are not equal. but all the elements in set A are in set B. Okay. Look at the, if anywhere you need a question, you want to ask a question, feel free. Look at a second example. Set A is defined in a, in a generator notation, all X such that X is a letter in a word proof. So it has, now, in order to be, so the letter is PROOF. Set B is all Y such that Y is a letter in the word roof. Now, is A a subset of B? Well, let's look at that. No, it's not, because A has letter P, while the set B doesn't have P. You can say B can be, B can be a subset of A, but not a subset of B. You follow me?
Yeah, I'm following. So what if in case, let's say, for example, B was proofs with an S, then A would be a subset?
Yeah, yeah.
Okay.
Yeah. As long as, the way we define the members of set, the first set, all those members are in the second set, then we can say it's a subset.
Okay. I think the only thing that was throwing me off on that one, I don't know why, but when I see X and then on the other one I see Y.
No, these are just symbols.
Okay.
You see, these are the alphabet of language of mathematics.
Okay.
So you have to get yourself used to look at math as a language, and you're learning grammar and you're learning vocabulary. That's basically what it is. Okay. And the grammar tells us the rules, how these symbols and how different operation actually act. Now let's look at example, the third example, example C. Set A is defined as all X such that X is a planet of Earth's solar system. Set B includes Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Then the question is, is A a subset of B? Yes, because all the elements, all the elements of set A, all the planets of, you pick any planet of solar system is included in set B.
So even though it wasn't spelled out like the other one was, it's basically telling you the Earth's solar system, which is indicated on the left-hand side. You can see all the planets there. So
yeah.
We would say that it is.
So because I defined, or the textbook defines set A in this way, we want all X such that X must be one of the planets, one of the planet of solar system. And set B is defined that has all the planets. So we can say set A is a subset of set B.
Got it. Okay.
All right. Sorry. Now we have proper subset, if set A is a subset but not equal to set B, then we say A is a proper subset of B. So if A is a subset but not equal, like the example of the planet that we just mentioned, if set A includes Mars and Venus, okay? Now, set A is subset of set B because set B has all the planets. But set A is not equal to set B. It doesn't have all the planets. It only has two of them. But therefore, it's a proper subset of B. I think on page 58, just a page before of what on page 58, for example, on the bottom of the page, it talks about definition of proper subset of a set. then it gives you an example, those blue color examples. Set A is 1 and 3. Set B is 1, 3, and B. Therefore, it is called set A is a subset of set B, and every element of A is also in set B. And we can also call it a proper subset because if they are not equal. So we can either use this symbol or this symbol. When we use this symbol with this equal sign, it means A is a subset of B. Every element of A is also in B. And when we use only this sign, it means even though A is a subset of B, but it's not equal to B. Therefore, it's a proper subset. So when you only have this, it's used for a proper subset. Okay.
So the one with the, so just to confirm, so the one with the line in the bottom means that it's equal to.
It means it's a subset, and it's also equal. And when it's a subset, no, it doesn't mean it's equal. It only means it's a subset. Because, for example, in the example, look at the textbook. Set A is 1 and 3. Set B is 1, 3, and 5. They are not equal. But it's saying that set A is a subset of set B. But in order to find out whether it's a proper subset or not, set A must not be equal to set B, which in this case is not. Therefore, we use that symbol without a bar. We can use both, both symbols are used for these two sets in the textbook. The first time when it's used, it shows that it's a subset of B. The second one that is used without the bar, it shows that it's a proper subset.
Okay, so that makes sense. I guess the only thing that's throwing me off is why are they using two symbols to basic? I guess that's what I'm getting.
Okay. It's just the first symbols only tells us it means it's a subset. The second symbol tells us it's not only a subset, it's a proper subset. It tells me that their elements are not equal.
Okay.
All right. So let's continue. Now, we talked about the empty set. The empty set is a subset of every set. The empty set is when the member is a null. Now, nothing can be member of every set. So, for example, if you have set B, this empty set is always a member of any set. And also, the empty set is a proper subset of every set except for itself. For any set B other than the empty set, so talking about the empty set, the null or the empty set is a subset of every set, and is also the proper subset, except when it comes to itself. You look confused. I'm
trying to understand it. It's a little bit confusing. So I guess the part where I'm when it's okay, except when it's for itself.
Because if it's itself, then it becomes equal, and you can have a proper subset. Remember, we talked about the proper subset here. Proper subset must not be equal.
Okay.
All right. I think if you practice a little bit and go over them, it becomes more clear.
Yeah, I think it'll once I keep practicing, I think it'll click.
Good. Now let's talk about these diagrams or complement. These are in fact very good for ministry in analyzing your church congregation and or the population of people. Let's say you're in a city, or whether you're as a missionary working in another country, in an area, these can be very helpful in targeting the people that you want to reach out with the gospel. We have it, let's say here in this circle, we have set A. When something is not in this set A, it's called A prime. And these two together form the universal set. The complement of set A, called A prime, is all the elements that are not in set A. And together they form the universal set. An example, the universal set that I talked about students at Southern California Seminary, okay? Now, I can have a set of all full-time students, and the A prime for that would be all the part-time students, because full-time and part-time students form all the students, and that gives me the universal set. All right. Now, you can have intersections and unions of these sets. Intersection of set A and set B is symbolized by this symbol. Like here, if you have these three circles, red, green, and blue, the intersections between set A and set B is this area. When I use the intersection, means the elements that I'm looking must be in set A and must be in set B. Okay, you know, when I use this symbol here, intersection between B and C, all the elements that are in set B and all the elements that are in set C, but I don't want, you know, nothing, I'm not talking about set A, so I don't want to have anything to do with set A. So it would be only section between B and C, only here without A. Okay. Now, union is just a reverse. The union of set A and set B is symbolized by A and U here, is set containing all the elements that are either in set A or in set B, or on both sets. For example, if I have set A here and set B here, the union would be this whole thing. That's a union operation. Okay. Now, there is this thing called Venn diagrams, and as I mentioned, these are very helpful for analysis and visualizing different problems. So you have these three different sets, set A, set B, set C. Then, for example, you have, when I talk about set A, this here, it includes the little a, little d, little g, and little e. Set C, capital C, includes the little c, little e, little g, and little f. It has the intersections with these two other sets. Same here. Okay, and outside there is none. Okay. So let's, for example, look at in a more practical way. Let's say we have a team that plays soccer and a team that plays tennis. These are the members of this set and this set. These are there are 4 people in the soccer team and 3 people in the tennis team. Now the union would be a set that does whatever, soccer or tennis. So it includes all of them. It includes Alex, Casey, Drew, Hunter, and Jade. That's a union. But the intersection means only the elements that do both of them. So it would be Casey and Drew. That's what you see here.
So
okay.
In that case, Casey and Drew are the only ones that play both soccer.
That's right.
Okay.
That's right. That's right. So union is in either set, then intersection must be in both set, And when we use minus or difference in one set, but not in the other. Let me show you. Let's say we want to have 3 sets. One group plays soccer, one set plays tennis, and one set plays volleyball. Now, in the one that plays volleyball has these members, Drew, Glenn, and Jade. Okay, so if I put them in a Venn diagram, I put, S, T, and V. Here, let's look at the volleyball. Glenn, okay, here you can see, where is Jade? Here. Jade here plays tennis and plays also volleyball, but doesn't play soccer. Alex and Hunter, they play soccer, but they do not play either tennis or volleyball. They're here. And when we come to the tennis, you see here, there is nobody that plays only tennis. Everybody plays tennis plus something else. Okay, and you see this part empty. Now, set S, if we want to define set S, would be Alex, Casey, Hunter, and Drew. These are all the people that play soccer. The union of the T and V, the tennis and volleyball, means all the members that play either tennis or volleyball would be T, union V, would be Casey, Drew, Jade, and Glenn. Okay. Intersection of sets S and V, meaning we want members who play both soccer and volleyball. There's only one person, and that's Drew, who plays both soccer and volleyball. So we say S intersection V, then equal to we put the braces, and the only member is Drew. All right. And let's see the empty set. Then if we want to, what the empty set means, it has no member. So the intersection of set S and V, the intersection would be Casey, Drew, and Jade, minus T, minus the members of the T. Now the members of the T is Casey, Drew, and Jade. So if I put a minus here, then the set is empty. There's no member. You follow me? See, what is set S? Set S has Alex, Hunter, Casey, and Drew. Okay. I want the intersection between S and T. So I want the members that are in both cases, both S and T. The only members in both of them are Casey and Drew. Now, if I say, no, but I want that to be subtracted, the difference between that and set T, I want to take out, I'm sorry. Set T. I was looking at it correctly. I want to take out the members of the T, so I have to take out Casey and Drew, so nobody's left. So you have no members who play both soccer and tennis, but you don't have any person who plays both soccer and tennis, but not tennis. You follow me?
Okay. Yeah, I have to think about it for a while, but yeah, I get what you're saying.
All right. Now the universal set, it says everybody who are in these three, S, T, and V, plus people who are outside, like Blair, Erin, and Francis, and Ira. So the universal set, we write it as U is equal all these guys, all of them. And in this case, has 10 members. Okay. Let's say if we want to set everyone who does not play the soccer in that universal set, that universal set is given to us. And the question is this: we want all the people who do not play soccer. They can play tennis, they can play volleyball, or they can just play nothing. But we don't want them to play soccer. Now, the ones who are play soccer in set S are Alex, Hunter, Casey, and Drew. So we take these out. All these, this whole section, the purpose section, would be the answer. Would be Blair, Erin, Francis, Ira, Glenn, and Jade. Okay. Now, complement. If, for example, if you have a set S, its complement would be S prime. So everything that is not S, S prime. So if this is set S, Alex, Hunter, Casey, and Drew, everything is not S would be its complement. It would be the answer to the previous slide. Everyone who does not play soccer would be S prime. Okay. Let's look at page 68. The example 3 set, let if U is 1, 2, 3, 4, 5 till 9, and A is 1, 3, 4, 7, it tells us find A prime. So U is our universal set. We want to find all the members who are not in A. So how can we do that? We look at set U and just cross all the numbers that you can see in set A. 1, 3, 4, 7. So A prime is a set of these numbers, 2, 5, 6, 8, and 9. Okay. Now, here I'm trying to explain why are we studying sets, because set, it helps us to treat a collection of mathematical object as a mathematical object itself. And it's basically a vocabulary. It's a starting point for forming definitions. And as you go to algebra, statistics, we need terminology, we need vocabulary to be able to communicate. And sets help us to deal with objects as mathematical objects. We will now, don't worry about this. We will talk about, again, importance of sets and function. Function is a rule that maps numbers to other numbers, but the question is this: what's the rule? We have to define that in mathematics. For example, if you see this example here, 2x plus 1 minus 1, it's very important to know the rule, the function, how it works. So the rule, for example, we are getting ahead of ourselves. Always you start here. You have to multiply 2 by 3. For example, if it was 2 times 2x, 2 times 3 plus 1 minus 1, you couldn't do the addition first and multiplication second. What I mean, let me show you. Let me show you with this tablet here. What I mean here. Stop sharing and go in here. Okay. What I was trying to say is, for example, if it was 2x plus 1 minus 1, if I had a number, for example, 2 times 3 plus 1 -1, first you have to do this part. You have to multiply these two numbers. It should be 6 plus 1 minus 1. The final answer is 6. It's a mistake to try to do this part first. In other words, it's a mistake to say 2 times 3 plus 1, 4, then minus 1. Then your answer would be 7. And that's wrong. This is a mistake. So the function, we have like a language. We have vocabulary, terminology, and then we have grammar. The grammar of a language of mathematics is this, that when you have this situation like here, where am I? When you have this here, 2x, first you do this part before you do anything else. Okay?
Yeah, that makes sense. I have one question though. So where it says 2x, so do you automatically multiply against the next number?
Yeah. Whenever you have this kind
3x, and it would be 3 times 4?
Yeah, 3x, whatever. This means 3 times x, whatever x is. If x is equal to 4, 3x means 3 times 4, equal to 12.
Okay, but you do that before you start doing the rest of it. Okay.
That's right. That's very important.
Okay.
Now we will get to that later on, but I'm just was trying to explain the importance of set and why we are memorizing them at this time. Okay. Let's go back to our PowerPoint. Okay. Again, now we will talk about this. I'm getting ahead of ourselves. In chapter 6, we'll talk about domain of function. A function maps numbers to numbers, but the same concept of a rule that maps things to things pops out all over. Operators, multiplication is an operator. Addition, division, these are all different operators. Maps functions to numbers. You can have abstract group of elements to other elements. We will talk about these more as we go in the chapters. All I'm trying to say in this part is this, that you have these, when we come to functions and operation, it's like the grammar rules for a language that relates words together so that we can make sense in a sentence. And sets are very powerful because in algebra, or topology, you have sets of, you use a set with operation to do different algebraic function or topology. The whole power of modern algebra is that it can apply to a set of anything as long as you define the operation and you obey the rules of that operation. Now, that was the part about sets, subsets, and the importance of them. Now let's talk about number system. There are different number system. This is Hindu, Arabic, Romans, Greek, and different Egyptian, Mayan, Babylonian, Chinese. There are different number systems. The number system that we use is Hindu Arabic, and it's very powerful because it has a number symbol for 0, and it can do major operation with less digits. Now you can see that as you go, if you look at those videos and as we go even in this PowerPoint. So let's first talk about system of numeration. When we talk about a number system or system of numeration, What we are talking about is a set of basic numerals and rules of combining these numbers, these digits together. A very important thing in different numeral system is a place value or positional value. It means that a symbol or a digit, depending where it's placed, has a specific value. For example, in our numerical system, Hindu Arabic numerical system, when we use, for example, the 20, the number 2 in the digit 2 in number 20 represents 2 tens. The first part is just the singular column. The second position is a 10 column. This first column is the column 1. The second column is column 10. A true, and this is very, very important for a numerical system to work properly and efficiently. A positional value system requires a base and a set of symbols, including 0 and 1 for the counting numbers less than the base. And again, the most common positional system that we use, the base that we use is base 10 or decimal number system. Now let's talk about Hindu Arabic numerical system. Oops. In Hindu Arabic numerical system, it is powerful because it requires fewer symbols to represent numbers as opposed to other systems. Basically, you have these 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can make all the other numbers just by these 10 digits. It's powerful because it has 0 and it can even deal with numbers less than 0. And it's base 10. Numbers 1 through 12 have unique names. Then, as you know, 13 through 19, you usually put teens after them. Numbers, for example, for the numbers 20 through 99, the tens place is named first, followed by the number from 1 through 10. For example, if you have 45, the 10th place, 4 is in the 10th place, so we say 40, and then we use 5, one of these digits. From 100 to 999, there's the combination of hundreds and the previous numbers. These are very simple and I think very clear. Like for example, here we have 440 or 100, 570, 5,083, 56,000. That's how we call them. Now, important other thing is exponential numbers or exponential notation. What you have is a b to power of n or b factor. When we write something like that, is an n must be a natural number. B is called the base, n is called the power. It's called the nth power of b, meaning that you multiply b by itself nth time, whatever n is. If n is 2, you multiply b 2 times. And when you write a number like this, b to power of n, this is called exponential number. Now, 2 things to remember: b to power of 1 is equal to b, and any number to power of 0 is 1. Any number to power of 0 is 1. Let's look at page 195. If you look at page 195, the top of the page, example 1, for example, you have 10 exponent 2, 10 to power of 2. That means you multiply 10 twice. 10 times 10, 100. The second example, 10 to power of 3. You multiply 10 3 times, 1,000. To power of 4, 10,000. 2 to power of 6. You multiply 2 6 times by itself, equal to 64. 1 to power of 7 is 1. 1 to power of any number is always equal to 1. And any number to power of 1 is just itself. 7 to power of 1 is 7. And remember, any number to power of 0 is 1. Okay? I know it's maybe too much information, but go over them and digest them little by little, okay? All right. Positional value, that's very important in different numerical system. In our numerical system, Hindu-Arabic, these are the positional system. And if you notice, I go from right to left. This is the positional value, 1, 10, 100, 1,000, 10,000, and goes on. Notice something. Depending on where the positional value is, think of it and subtract 1 from it. Here is 1. 1 minus 1 is 0, so I don't write it. Here's a second position. 2 minus 1 is 1, so you have 10 to power of 1. This is a third position. 3 to power 3 minus 1 is 2, so it's 10 to power of 2. Do you follow me? Okay. And to evaluate a number in Hindu-Arabic system, we multiply the first digit on the right by 1. We multiply the second by 10. What I mean is this. Look at this example. When we write 572, if I want to expand that, to open it up, basically that's what I'm saying. You have these 3 digits, 5, 7, and 2. 5, 7, and 2. Now, our base is 10. That's the base 10 numerical system. The first one, we go here, we start from the right, multiplies by 1, then multiplies by 10, multiplies by 100. In a way, this is also 10, but 1 minus 1 is 0, and any number to power of 0 was 1, remember? So we get 2 times 1. This is second position. So we have the position minus 1 is 1. So it's 10 to power of 2 minus 1, which is 1. So we get 7 times 10. 500 plus 70 plus 2 is 572. You follow? Okay. Now, this is actually what I meant by expanded form. You might have a question that gives you a number and tells you to write it in an expanded form. You multiply the digit in the nth place from right by 10 to power of n minus 1. That was the thing that I was explaining. For example, I think an example explains everything better. If you have this number, 1,234, and the question asks you, write it in an expanded form, this is what you do. First, write the digits, 1, 2, 3, and 4. 1, 2, 3, and 4. Our base is 10, so multiply by 10, multiply by 10, multiply by 10. And this one is 10 to power of 0, which becomes 1. So now, don't worry about this exponent. We will find that out. The first one is 4 times 10 to power of 1 minus 1, which makes it 0. So it becomes 1. This is second position. 2 minus 1 is 1. So it's 3 times 10. This becomes 2, and this becomes 3. Do you follow me? Or I can show it to you, show it on the tablet if this is not clear.
Yeah, I'm sort of on, but yeah, I would, if you can show it to me on the tablet, I think it would
Okay.
help.
Yeah, yeah. Let me do that. You know, for example, we have this number 134. Let me stop sharing, go to the okay. All right. Okay. And just go here and let me get this clean up here. All right. What I was saying is, if are you here?
Yeah, I'm here.
Oh, okay. Can you see me?
I can see you and the tablet. I mean, and the screen. Yeah.
Okay. All right. If we have, you know, the question asks us to write the number 1234 in an expanded form. Okay. You can write it as this. Take the digits 1, 2, 3, and 4 and just write them 1, 2, 3, and 4. Okay. Now, as we start from the right side. This is base 10. So, okay, they all must be multiplied by 10 and parentheses plus times 10 parentheses plus times 10 parentheses plus times 10 parentheses plus. Okay. So all I did so far, I just took that number, I put the digits here, 1, 2, 3, and 4. Our base is 10, so they must be multiplied by 10. Now I need to find the exponent. Now remember, you start from the right-hand side or from here for this. This 4 is in the first position, position number 1. The rule is this. To find the exponent, to find n, take the position and subtract 1 from it. 1 minus 1, that's the first position, yes? So 1 minus 1 is 0. So I go here for 4, it should be 10 to the power of 0, which is equal to 1. You follow me?
Yep.
Okay, now let's go for the second one. I want to know what should I do with the exponent of the 10 there? What position is this one? Tell me.
That's the 10th, right? The 10th.
Yeah, the 10th or the second position. This was the first position. This is the second position. So second position minus 1 equals to 1. So the exponent here should be 1. Okay. Now let's go to the 2. We want to find out what should be the exponent for the 10 here. What's the 2? What kind of position is that? What position is that?
Third position.
I'm sorry?
The third position?
Third position minus 1 equals to 2. So the exponent for here should be 2 for the 10.
Okay.
And how about 1? What position is that?
That's the fourth position.
Minus 1 is 3. So the exponent here for 10 should be 3. So I have 1 times 10 to the power of 3, which is 1000. Let me write it here. 2 times 10 to the power of 2, which is 100, which is 200. Then I have 3 times 10 to the power of 1, which is 10, times 3 will be 30. 10 to the power of 0 is 1, so 4 times 1 is 4. That's what I get, 1234. That's the expanded form for that, or like here. You follow?
Yeah, I get it. So what you do is you do the position minus the 1.
Yeah, to find the exponent for that base, which is base 10.
Okay.
Good. Okay. So let's go to our PowerPoint. Okay. Okay. Now, these are Babylonian numeration system. We have, these are, again, Babylonian numeration system. Oops. Their numeral system was a place value, but a base 60 or hexadecimal system. It's not a true place value because they didn't have a symbol for 0. And that's why these numerical systems fail. And I truly believe one of the reasons that these cultures also fail had a lot to do with their mathematical system. Of course, there were many other elements involved, spiritual, moral, political, but you can operate with a numeral system which is base 60 and you don't have any symbol for 0. No, when it says no, you see, when we talk about base 60, it means this. Instead of 10, the first one will be always 1 because you have n minus 1, 0. But then instead, the second position would be 60. The third position would be 60 to the power of 2, and the fourth position 60 to the power of 3. Let's look at pages 197 and 198. Okay. If you look at page 197, and before example 4, look at the little paragraph above it. It talks about the Babylonian numeration system, talks about how in the city of Babylon, which is nearby the city of Baghdad in modern-day Iraq, they formed this balanced numerical system about 1400 years. It lasted for 1400 years, and between 2000 BC and 600 BC, they formed this numerical system. As you can see in our textbook, they have that table 4.1 for symbols, like that little symbol, like a V shape, is equivalent to R1. The other symbol, which is like less than, is equal to number 10 in our numerical system. So look at that example, actually right above example 4. It has that V shape, then this V shape kind of rotated, and then 2 V shape next to each other. The V from the table, I mean, this is something that you have to, it must be given to you, means 1. Okay, we want to know, for example, if you have that number, you find a tablet in Babylon, and there are these symbols written on it, and you know those symbols represent what kind of Arabic numerals. You want to know what that number represents. Okay, you first kind of translate that into our numeral system. It is the first one. Actually, it starts from the right-hand side. The 2 V that are next together, each V is a representation of a 1. When they are next together, means 1 and 1, or 1 plus 1. The second one is a representation of 10. So 10, and the third one is again a V, which is representation of a 1. Okay. Now I go to the base. Now I want to find out by what number I need to multiply them. It's a base 60. So the first one 1 plus 1 times 60 to power of, now you tell me, what's its position?
That's gonna be in the second position, right?
No. We're starting from the right. It's a first position. So it's 1 minus 1, which is 0. Any number to power of 0, whether 10, 60, whatever, is 1. That's why you have 1 plus 1 times 1. You follow me?
Okay, are you which one are you looking at? Because I think I'm looking at the wrong one. I'm on the right page, but
The middle,
197, right?
right,
The page
right above example 4. You know, in the
Okay, I
middle.
was looking at example.
No,
Yeah,
no,
I
no.
see it now. I was looking at the one below that.
No.
Okay,
Now
I
let's
see.
look at that, then we go to
Okay.
example 4. So you have 1 plus 1 times 1, okay?
Okay.
And you know where that 1 comes from.
Yeah, that's gonna be from the first.
It's a first position, so
Yeah.
you take the first position, n minus 1 is 0. 1 minus 1 is 0.
Right.
Any number to power of 0 is 1. So you get 1 plus 1, which we get it from the symbols, times 60 to power of 0, which is 1. So we get 1 plus 1 times 1. Okay? You follow? Now
Okay.
look at the second part, and we go from right to left. That symbol, kind of a less than symbol, is equivalent to number 10 in our system. Now, what position is that?
The number 10?
Yeah, when I moved to the second symbol from right to left, what position am I? Where am I? Position, as far as the position. You're in the second position.
The second position?
Because remember, the first part, the 2V shape, is first position. Remember, like,
Right.
maybe I can show you. Here, remember, if you look at the screen here, you see, this is a first position, this is a second position. Remember, the rule is this: take the position n minus 1. Now, we have 10 here because this is a base 10 numerical system. We have 60 here because this is 60 base numerical system. So when you come to, the first one from the right hand side, there are those 2 V's. You follow me?
Okay, I got the first 2 V's, right? And it's gonna be the first position. Okay.
Okay, which is, and a V is 1, so we have 1 plus 1 times, what's the base?
60.
What power for that position? 60 to power of what?
The power of 1, right?
No.
Oh, power of 0.
0. Why 0?
Because it's in the first position.
Yeah. First position, 1. Minus 1 makes it 0. So therefore, any number to power of 0 is 1. Now let's move from right toward left. We come to the second symbol, that less than V. Okay. That less than V is 10. Now, what position are we? Where are we as far as position?
We're in the second position.
Okay. So what's the base?
60.
Okay. So 60 should be to power of what? If you are in a second position.
60 is going to be to the power of 2, right? No.
Yeah. 2 minus 1, because you always subtract 1. Okay.
Gotcha. Okay.
So you get 1. Now, so it's 10 times 60 to power of 1. Now move again toward, from right to left. You come to the third column. and you have that V shape again, and V is 1 in our numeral system, but what position we are, what column we are.
We're on the third.
That's right. So you take the position n minus 1. What should be the exponent for 60?
2.
Exactly. And that's why you see that. You see 1 times 60 to the power of 2.
Okay.
And then you do the multiplication inside the parentheses, you add them up. So that number, that we and that strange shape that we, let's say we find it on a clay, is actually 4,202 in our numerical system.
Mm. Okay.
Now let's look at example 4. Example 4, let's look at A. Let's just do one of them. You have this strange shape symbols, okay? And you go from right to left. Notice they are put for us in 3 groups, meaning we have 3 columns. We have 3 positions. You follow me? Yeah?
I'm sorry, the internet was cutting out a little bit.
Okay. Okay, you see these symbols on example 4A, they are put in 3 groups.
Yes.
Okay, so we have 3 positions. We go from right to left. The first would be first position, then the second position, then the third position. Okay, now we want to find that number in our Arabic system. Do you want me to use the tablet? Would that be easier for you?
Yeah, I think that'll be easier. Yeah.
Okay. Yeah, let me go there. Okay. Okay. All right. Let me clean here. Okay. All right. See, we have I'm talking about example 4A on page 197. So we have these 3 groups of symbols in Babylonian symbols. 2V, and then we have this shape, and then we have okay. So we have them in 3 groups. This first one, it's the first position here. This what I have here. This is the first position, okay? So let's first of all write these things in our own numerical system. So we have those when it looks like less than, they are 10. Okay, so when you have 2 of them together, means we add them. 10 plus 10. Okay, that's for these 2 symbols. You follow? You follow?
Okay, yeah.
Okay, then we have 2 V's, and V was 1. So we have here +1 and +1. Okay, so basically, if I write these numbers in our numerical system, would be 10 plus 10 plus 1 plus 1. Okay, but then I have to multiply it by its base. And Babylonian system, we said, is base 60. Okay.
Okay.
So I put that there. But what is this position? The right side, this whole thing.
The first position.
Okay, so the position is 1, the first position. You subtract 1 from it, it becomes 0. So you have 60 to power of 0. So and 60 to power of 0 is 1. Okay.
Okay.
And if I add 10 plus 10 plus 1 plus 1, it's 22. So that takes care of the first part. Okay. All right. Now let's move here to the second position. we have this little v here, which is 10. And then, I mean, like a less than symbol,
Yeah,
and then a v, which is 1. So we have that. Now, again, what's the base?
60.
What's the position?
The second.
Second. So second minus 1. So I get 10 plus 1, which is 11, times 60 to power of 2 minus 1, which is 1. Okay. This is equal to 666. Okay. Let me get rid of this thing here.
Okay, because you're doing 11 times 60.
Okay.
Right. Okay. Gotcha.
Now let's move here to the farther from right to left. We have 2 of these v, and each v was a representation of 1. Okay. So I have 1 plus 1 times, what's the base?
60.
60. What's the position?
The third position.
So therefore 3 minus 1
Equal
equal to 2. So I have 1 plus 1, 2, 60 to power of 2, which is 2 times 60, 300, 360, 3600. I'm sorry. Okay, so this we will get, and this is equal to 7200.
Okay.
Okay. So now you add these things: 7200 plus 660 plus 22. And the final result is 7,882.
Wow. Okay. Yeah, that made more sense when I seen it written out like that.
Okay. Okay. We do that. If that helps. Okay.
Yeah.
Do you need any break?
Yeah, if you don't mind, if I can take like a quick 5-minute break, I gotta go.
Sure, sure. Let's take 5-minute breaks and we come back.
Okay, perfect. Thank you.
Sure. Okay, I stop this. Okay. And we don't have, a few more slides to cover and then we are done. Let's go to share screen. Okay. And we were here. Okay. Actually, yeah, I think we were here. So you followed that example from the tablet.
Yeah, that made sense to me. When you were talking about earlier in the text, I wasn't really getting it, but when you showed me on the tablet, it made more sense. So thank you.
You see, the key is this: whenever they give you a number in whatever numerical system, write the digits. Then, or if there's symbols, you need to translate them from, like Babylonian symbol to our numerical system. Just remember, when there are 2 symbols are next to each other, it means plus. And then based on the base 60, so you multiply them by 60. Now, in order to find the position, the exponent for the position, remember, it's wherever it is, the position minus 1. So if it's the first position, 1 minus 1 is 0. So any number to power of 0 is 1. Then the second position is second, 2 minus 1 is 1. So it's, if it bits like here, if it's base 60, would be 60 to power of 1. This is a third position, 3 minus 1, 2. Fourth position, 4 minus 1, 3. And you, after you have translated those symbols into our numerical system, you multiply them by these 60s to power of whatever position they are. Okay.
Yeah, no, that makes sense. On the videos that you have on the popular, do they explain this?
To some degree they do, but it will help you. It will help.
Okay, but you're recording this, so you're gonna.
Yes, yes, this will be
Okay.
also available to you. The last year session, well, I'm not sure if I will keep that, but this will be available to you also.
Okay.
Let's, for example, now let's move on because I don't want us to take too much time here. Let's move on to now another numerical system is Mayan numeration system, and here is these are given to us on page 198 of our textbooks. Talks about that, about the Mayan culture, which expanded from South America all the way to Mexico, Belize, Guatemala, and they have these numerical system. They were excellent in mathematical knowledge and excellent in arts. And in fact, the advantage of their numerical system is they had a symbol for zero. That's it. And that really helps. Now, if you look at page 198, look at page 198, that table 4.2, it will be given to you. There's no way that we can memorize that. It tells you whenever you see these symbols, what they mean, what they are equivalent in our numerical system. And the place value system for them is base 20. But again, the rules is the same. The position of that, whatever position it is if it's a first position, n minus 1. First position, 1 minus 1, 0. So it's 20 to power of 0 is 1. Then 20 to power of 2 minus 1 is 20. And it goes on. Do you see that on page 198?
Yeah, I see it.
Okay. All right. Now, let's, they had these are discovered by archaeologists. Let's, okay. For example, here, of course, I simplified the numbers, but actually, before we do this, let's look at the one that we have in the book, the example number 5. And let me do it on the tablet. So let's go to the tablet. And let me clean this up. Okay. All right. If you look at example 5 at the bottom of page 198, it gives you those Mayan numeral system. Let's look at only example A. You know which part? Do you know what I'm talking about?
Yeah. Okay, I see it.
Okay, so
98, right? On page 198.
Yeah, the bottom of page 198, example 5, and A, the example A. Okay, so we have these. Let me draw. I try to draw them here. So this is the first one with 4 dots. 1, 2, 3, 4. Then the number, this oval shaped thing. Okay, then we have the line with 2 dots. Then we have 2 lines with 2 dots. Okay. So we have these symbols. That's a number that we find in, let's assume, in a Mayan clay. We want to find out what that would be in our numerical system. We want to find its equivalent, okay? So we look at the table. We need that table to understand. We see this sign here. That's on 14. That table is 14. Okay. That sign over here is 0. The other sign is 7. And this sign is 12. Okay. Okay. And we know they are base 20. So, just multiply by 20, multiply by 20, multiply by 20, and multiply by 20. Now, always remember, we said we go from right to left, and when you have these numerical systems that are vertical, we go from bottom to up. So in other words, this one here is position 1. This is position 2. This is position 3. This is position 4. Okay?
Okay.
And remember the rule, whatever the position, if I call n the position minus 1, it gives you the exponent for these things. So if this is position 1, so I have 1 minus 1 equal to 0. So I have 12 times any number to power of 0 is 1. Okay? Do you follow me?
Yeah.
Okay. Now you got to the second one. 20. What's the position?
That's the second position.
So 2 minus 1 equal to 1. So I get 7 times 20 to power of 1. Now let's go here. What is this position?
Third position.
Okay, 3 minus 1 is equal to 2. So it's actually 0 times 20 to power of 2, which equals to 0, actually. And this is fourth position. So 4 minus 1 is equal to 3. So we get 14 times 20 to power of 3. Okay? Did I get it right or no?
Okay.
No. Something 8. No, why did I? Oh, I'm sorry. I said, wait a minute. Oh, I'm sorry. Down. They have a different rule. Oh, I forgot. First, second, third, fourth. Okay, first, second, third, fourth. So this should be oh, 1, 2, 3, and 4, 14. 1, 2, 3, 4. To power of 1. To power of 1. 18, 20. Oh, wait a minute. I missed something here. Wait, 12 to power of 1, 7 times 20. Then I get 18 times 18. Okay, their system 18 times 20. The place value, okay, the place value is different. The third position is not that simple in the Mayan system. The third position, you got to look at that table, is 18 times 20 to power of 2. So I need to change something. The third position, actually, let me do it with this. Okay. So sorry about that. Yeah, I made a mistake here. Sorry. Okay. That rule n minus 1 equal to exponent doesn't really apply for Mayans. You got to just keep in memory the numbers here. Are you following me?
So even though so 20 was the base, so we're doing 18 now?
Yeah, you see here, if you look at that page 198, below the table, it tells you, it gives you the numerical value for the symbols, and then it tells you the positional value. That's something that we just need to accept it by the information that archaeologists have found out. Has nothing to do with mathematics, just that's how they design their numerical system. If you notice on page 198, above example 5, the first position is 1, which that's what we get. The second is also fine, but when it comes to the third one is fine too, because because wait a minute. No, you see the third one, then you add, suddenly they have put, as far as the position is concerned, they had let me make this a little bit oh, okay, the size. You see here, if you do, you see that on the top of at the top of example 5, you have the first position, and the second position is fine, but the third position is 18 times 20. That's the way they just put it. And the fourth position is 18 times 20 to power of 2. That just, you got to just remember that. Okay?
Okay.
Do you see that?
Yeah, I see what you, so the first one's 1 and the second one's 20, and then the third
Yeah,
one.
the first one, and the first and the second position follows like the rule that we have, you know, the position minus 1. But once you go to the third position, they had different the positional, and that's, you see, that's whatever the culture assigned to that position, the assigned value for the third position in their numerical system was 18 times 20. And the fourth one was 18 times 20 to power of 2. So it looks like they subtract from whatever the position is, they subtract 2 instead of 1. So that's why they get in the fourth position, they get 2. And in the third position, they get 1.
Okay.
And then you do those multiplication, and you have those values on the side. This becomes 100,800, and this becomes actually 0. Any number times 0 is 0. This becomes 140, and this becomes 12. And then you add them up, and you get the total value of 100,952. Sorry for the mess. Can you follow me? Do you understand what I did?
Yeah, I get it. So on the Mayan one, we have to change it up a little bit. We have to remember that it's not the same as the.
Yeah, when it comes to Mayan, yeah, the first and the second position is fine, but when it go to third and fourth, they're different. Now let's look at the PowerPoint example I had in the PowerPoint. Okay, let's. Okay. Okay. All right. Let's go to this example. I think that for example, if we have in a Mayan system, we have these symbols. Okay, we find their value. We know that when you have these two lines, that's okay. Okay, we have the line, the two lines with two dots above it is 12. You see that? I put that 12. The one just with the dot is a 1. This oval shape is 0. And then the two lines is 10. Okay, we get that from table 4.2. Now, we start from the bottom. This is the first position, so it will be multiplied by 1, the second by 20. Now, I simplified that. The third position, instead of 18 times 18 times 20, which is 360, I just rounded up to 400. And the fourth position, which is 18 times 20 to the power of 2, I rounded up to 8,000. Okay, so that's a number, and then you multiply them and you add them. So these symbols is equivalent to this Arabic symbol, numeral, Arabic number in our system. All right? Okay. Example 5. Oh, we did that. Actually, that's the same thing. We did that already. We have done this already. Okay. Then we have Greek numeration, numeral system that you need to, again, you need to have the table to know the value for each of these Greek alphabet. Roman numeral system, very, very inefficient numeral system. And the key to know, to use for this numeral system is this top blue line, blue bar. You know, the 1I is 1, V is 5. These are the key things. X is 10, L is 50, C is 100, D is 500, M is 1000. So, for example, if we have 154, let me get these things. Oops. 154, I wrote it is equivalent to CLIV. How did I get that? CLIV. Let me go. C is 100, L is 50, I is 1, and V is 5. So CLIV would be 151. Do you follow? Okay, so that's we get CLIV. 1492 is this one. I need to write it myself. It's MCC. Let's see. 1492. Okay. Let's see. If we go to, let's go back to our table.
Yeah.
M is 1000. So if I have 1400, so I have I need to have 1 M. Then 400, I need 4 C's next to each other. M, C, 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 C. Then 1492, and that L is 50, so I get L, and X is 10, so I get 4 of X, 1, 2, 3, 4, and I is 1, so I need 2I. So that's, let's see. Yeah, so you see, you get 1000 M, 100, 200, 300, 400. So you get 1,400, L 50, X is 10. So you get four of them, makes it 90 and 2, 1. Okay.
Oh, quick question. So when it, like, for example, on 92, I get why you're doing the L for 50 and then 4 X's for the 40 to make 90 and then 2. Could you write it as well, 9 X's and 2 1s, or you don't do that because
yeah, you can. You can. In fact, that's a good point. You see, let me show you something. If you go here to this table, once I get M for 1,000 and 4 C's for 400, in fact, you have 92 right here. So another way of writing that would be just saying XC111, XCLL, or II, I'm sorry, not L. So there are very many different ways to write it. Okay, I try to use the more simple one.
Okay, that makes sense. Okay.
Or, this one, 3,495. So 3,000, M is 1,000, so I need 3M. 400, so C is 100, so I need 4 of that. L is 50, so I need a L. And 90, I need 4X to make it up to 90, and V is 5.
Okay.
Okay. And how you can see how inefficient these systems are, Just think of trying to add numbers using Roman numerals or dividing numbers. It's crazy. Then you have the Hebrew numeral systems. Again, the key thing is remember this bar here. That's the key thing that gives you 10, 20s, 30s, and 40s, 50s. So in this system, when we come to, let's say, if I want to write 764, this in this system, and if let's say, now remember a couple of things about, and I get to 764 right now. It is not really they don't have a base, therefore they are not a positional numeral system like Roman numerals. They were not positional. If you want to find the number 764 in the Hebrew numeral, it is this number here. Now, why is it this number? Let's go to it. We start from right to left. This is 400, okay. So 400. This is 300. So I get 400 plus 300, 700. Then I need 760. This is 60. And this is the number 4 would be, where is 4? I just saw it, just in front of my eyes. Where am I? Oh, here. This is 4. So you have that alphabet, this plus 60, and the doll actually. So that's what it comes from right to left. Okay.
So on the Hebrew numerical system, the highest number that goes to is 400?
No. You can, if you look at this chart, you can have different combination and form different numbers. But let's say, for example, if I want to write 800, I need to use 2 of these numbers here.
2 of that symbol. Okay.
Yeah. Okay.
Yeah. So in regards to symbols, though, it only goes up to 400 on the symbol. Okay.
Yeah. On the verticals, the vertical column, and these are the going from 1, 2, 3, 4, 5, 6, 7, 8, 9. Multiplies of 9. Okay. So if I want, for example, If I want to have this here, would be 400, and that symbol is 49. 49. Okay. This is 49.
Which one's 49?
Right here at the bottom. Do you see that? Because this is 400. I mean, it's 400. It's 409. 409.
Oh,
not
409. Okay, I got you. Okay. Yeah. But if you wanted 49, then it would be on the column where it's 40 and then go all the way to the 9.
Yep, it would be this one.
Okay, that makes sense. Okay.
All right. Okay. Okay, now let me just, any counting number greater than 1 may be used as a base or a positional value numeration system. If a positional value system has a base B, then the position value will be like, we talked about this, you know, you take the position -1, you get 0, and any number to power of 0 is 1. Second position is power of 1, power of 2, power of 3, power of 4. For example, if you have a base that has, if a numerical system is base 8, 1, 8, 2, 3, 4. The only thing that kind of was crazy was the Mayan system. If the position, a numeral system is base 2, again, 1, 2, 2 power of 2, power of 3, power of 4. In computer, they use binary system base 2 and sometimes octal base 8 and hexadecimal base 18. Okay, in a computer programming. Now, the thing that is important is sometimes we want to convert from bases less than 10. Let's say if you have a number 453 base 6, that's not same as 453 in our system. We want to convert that to base 10. This is what you do. 453, again, write the digits separately, 4, 5, and 3. It is base 6, so they all must be multiplied by 6. Now this one is position number 1, so it's 1 minus 1, 0. Any number to power of 0 is 1, so you get 1. This is 2 minus 1, 1, 6 to power of 1, and 6 to power of 2. And you do the multiplication and addition, and you get 177. So 453 base 6 is actually 177 in our numerical system. Okay. Let's say if we want to convert a number 3615 base 8 to a base 10, again, write the digits 3, 6, 1, 5. Multiply by 8. The first position is always 0, so the number becomes 1. To power of 1, to power of 2, to power of 3. 1 less than its position. And when you do the multiplication and addition, that's the number in our base 10 system. All right. Okay. If we want to convert from base 2 to base 10, let's say we have this number 101, 101 base 2 to base 10. Again, write the digits 101, 101. It's base 2, so they all must be multiplied by 2. The first one is always 1, power of 1, which is 2, power of 2, power of 3, power of 4, and power of 5. This is 6 position. 6 minus 1 is power of 5. You do the multiplication and addition, the answer is 45. Okay. I think the other two are optional, and I'm not going to ask you a question on the test. This is on page 208 and 211. If you were interested to look at them, go ahead. But it might be a little bit complicated. It's has to do with when you want to do addition in other than base 10 system, like base 4, or you can take a look at it. If you had questions, you can ask me next week, but it asks you, for example, how to the right page, how to do addition in other than base 10 system. I'm not going to ask you on the test, but it's optional if you want to take a look at it. There's one there and one in 204. Basically, for example, the one on page 204, example 3, it says convert EC7 base 16 to base 10. That's just like the one that we did here. So, and we need to know these digits represent what number, and we have that table on the side of the example 3, page 204. E represent 14, C represent 12, so, and 7 is 7, so it's base 16. So again, 1, 16 to the power of 1, 16 to the power of 2, and you do all the addition and multiplication, and you get the final answer. But the second example that I put there, 208, on page 208, example 1, it asks you to add two numbers in a different base system. It's up to you if you want to take a look at it. It's optional. It's not going to be on the test or quiz or anything. But basically, you got to follow different rules for doing addition in different numeral systems. And because we are not going to work with these different numeral systems, I just put that as an optional example. Okay. Any question? If that's it, we finished.
On the quiz, we have
the quiz. The quiz, you got to know the sets, and there will be question about the Mayan system with the table. So I will give you the table. So, but you got to know the sets, understand the set, subset, things like that quite well. Okay.
And is that hold on, give me a second here. Is it a time quiz or something, or?
I believe there is a time limit, but you have enough time. Yes, all of the tests and quizzes, they have time limits.
Okay, and it's not available because I click on it.
Yeah, it should be available because some students have taken it.
Oh, we have. Oh, but we have to download the file, print it, and.
Yeah. You download that because it has signs and symbols. You cannot do it unpopularly. You download it, you write it, and then send it back to me.
Let me just make sure which one. It's not assignment number 3, right? That's different.
Yeah, let me get to it myself.
Oh, I think 20 questions, I think.
Yeah, just one moment. Okay. Wait a minute. Where? You can see my thing. Where? Hello. Where is this?
I can hear you, but I can't see you either. I don't know what happened.
Oh, something happened.
I think I can see you now.
Can see me now?
I can see you now.
Oh, okay. I don't know what happened. Let me try to Okay, I can't go there to pop. Oh, I should be able to, shouldn't cause problem. Yes, one moment, just.
I think I see it. I think it's like 20 questions, I believe.
Okay. Yeah, that's it. Yeah. Okay. Let me, okay, I finally was able to get there. Okay, let me just get to lesson number 2, and then let me go to share screen. Yeah, you see you have assignment 3, and then you have quiz number 1, which is very simple. Very simple. You're just matching.
So we're just drawing a line across to match?
Yeah,
okay.
Just match them.
Okay, gotcha.
Okay.
Okay, that makes sense. I was just wondering. And then the bottom one, that's just the answer to the comprehensive exam.
Yeah,
right?
For that
bottom, where that
puzzle in the from last week.
Okay, that makes sense. Okay.
All right.
That's it. And then we have to submit assignment number 3 as well. That one's.
Yeah.
Okay. Now we just print it out, do it on there, and then scan it and upload.
Sure.
Okay.
Yeah. Okay, brother. Well,
all right, perfect.
Okay.
Thank you so much, Professor.
You're welcome. Any question, feel free to ask me, and hope everything will go great for you. Have a good week. Okay.
All right. You too. Thank you, sir.
God bless you. Bye-bye.